During the spring of 2023, Riga Technical University will offer a course in system dynamics for PhD candidates and practitioners in the public and private sector who are facing complex dynamic challenges in their work. System dynamics is a scientific approach to model-based analysis of systems that develop over time and that are governed by a complex underlying systems structure. To that effect, system dynamics offers a wide variety of methods, techniques, and tools. This video is based on an interactive learning environment that you can access under the web address listed here. The approach was developed in the 1950s by Professor Jay Forrester at MIT. Forrester talks about the origin and purpose of this approach in a two-part video that you can click to see in the interactive learning environment referred to above or on the YouTube address listed at the bottom. The system dynamics method typically incorporates four phases: problem recognition, problem identification, problem solving, and knowledge dissemination. We recognize a problem by forming an expectation about the future development of attributes or variables of importance. The expectation is typically based on historic development. The problem is recognized by comparing the expected future development with the development we desire and one we might fear. We identify the problem by finding the system structure underlying or causing the problem that we've recognized. In part, this is done in communication with a variety of experts and stakeholders, commonly by way of group model building sessions. That system structure we capture or represent in a system dynamics model that consists of stocks and flows, as well as a variety of time-consuming and instantaneous relationships. Such a model constitutes our hypothesis. It explains what we believe is the structure underlying the current problem. Based upon an extensive validation process, the model will eventually be able to reproduce, by way of simulation, the problem as it develops over time, and the model thus constitutes a problem theory. We identify a robust solution to the problem we address by modifying the structure underlying the problem. We identify a new strategy that is a well-balanced set of policies that should govern the decision-making processes and thus cause a favorable change in the dynamic development of the system. Typically, this is done in an interactive hypothesis testing process leading up to a theory of change. Subsequently, we assess such a theory through a feasibility analysis and modify it from wishful thinking to an implementable solution to the problem at hand. We communicate effectively our insight resulting from the problem recognition, identification, and solution using model-based interactive learning environments. Such environments typically take the form of serious games by which experts, stakeholders, students, and members of the public at large are invited to explore and critique the representation of reality that the system dynamics model constitutes, and test out their own solutions to the problem at hand. They can do so individually or in groups where they take on the roles of various decision makers in the system. To illustrate the first two stages of this process, we will use an example where we address one of the imminent challenges facing humanity. Recently, WWF documented in their report, Living Planet, the loss of biodiversity that we've experienced over the last 60 years, resulting from a loss of global carrying capacity. We will use a system dynamics model to illustrate how the reduction of a population of a single species may be recognized and identified. The focal point of the problem we're presented with is a favorable population growth, followed by a sharp decline. We start our modeling process by introducing a stock that represents a population of individuals. As seen from the simulation, the stock contains 1,000 individuals, and there is no change in the stock level. So far, there is no dynamic development that can explain the reason behind the problem at hand. So we continue the modeling process. We then introduce a flow of individuals entering the stock. This flow represents the births of individuals adding to the stock level at a certain rate. Thus, over time, the flow will trigger a dynamic development in the system. The rate of the birth flow is determined by the number of individuals currently in the stock, that is the stock level, and the total fertility of those individuals. The fertility is assumed constant. We may choose a fertility by clicking on the semicircle above the variable. Any fertility value different than 0 will trigger exponential growth in the system. The larger the population is, the larger is the positive contribution in the form of births per month, and the more will the population have grown next time around, that is, by next month. We see that the population level and the birth rate interact in a loop that reinforces the population development. We call this a reinforcing or a positive feedback loop. So far, the model is not able to reproduce the problem at hand. So we continue the modeling process. We then introduce another flow of individuals, this time leaving the stock. This flow represents the deaths of individuals, subtracting from the stock level at a certain rate. Thus, over time, the flow will modify the dynamic development of the system. The rate of the death flow is determined by the number of individuals currently in the stock, that is the stock level, and the total mortality of those individuals. The mortality is assumed constant. For now, leave the fertility at 0 and choose a certain mortality by clicking on the semicircle above that variable. That will trigger an exponential decay in the system. The smaller the population is, the smaller is the negative contribution in the form of deaths per month. And the less will the population have diminished next time around, that is, by next month. We see that the population level and the death rate interact in a loop that dampens the population development. We call this a balancing or a negative feedback loop. Even now, the model is not able to reproduce the problem at hand, so we continue the modeling process. The dynamic development of a system is determined by the interplay between its feedback loops. In this case, a positive and a negative loop. In complex systems, there are typically a variety of such loops, all interacting with each other in the creation of the system's development over time. To investigate this interplay, notice that the significance of the two loops in our system is characterized by the fertility and the mortality, respectively. Notice also that we have introduced the net growth rate, that is the birth rate minus the death rate. As long as the fertility is equal to mortality, the significance of the two loops remains the same, and they compensate for each other. The birth rate is equal to the death rate, and the population level remains constant. The system is in equilibrium. Now we increase the fertility above the mortality. That causes the positive loop to dominate the negative one, so as to govern the dynamic development of the system, causing population growth because the birth rate is larger than the death rate. Then increase the mortality above the fertility. That causes the negative feedback loop to dominate the positive one, so as to govern the dynamic development of the system, causing population decay because the death rate is larger than the birth rate. In both cases, notice the development of the net growth rate. Again, the problem development has not been reproduced, so we continue the modeling process. We then introduce the carrying capacity. That is the capacity of the environment to support a population with food, shelter, etc. The carrying capacity of the environment corresponds to the maximum population that the environment can support. If the population is smaller, then the population will grow towards the carrying capacity. If the population is larger, then the population will decay towards the carrying capacity. Moreover, we introduce the stress that the population experiences, represented by the ratio between the population level and the carrying capacity. If the two are the same, then the stress amounts to 1. Again, we experiment with the fertility, the mortality, and the carrying capacity to investigate the resulting population development and the associated stress. Noted that so far, the stress has no impact on fertility nor on mortality. In reality, however, that is not true. Notice that the population may develop beyond the carrying capacity with no apparent consequence other than the inevitable elevation of the stress level. Therefore, we must continue the modeling process. We then introduce a nonlinear effect of stress on mortality and fertility, respectively. These effects are characterized by clickable graphs at the bottom of the screen, indicating that an increase in stress will cause a decrease in fertility and an increase in mortality. Over time, this will cause a shift in feedback loop dominance from the reinforcing positive feedback loop towards the balancing negative feedback loop. The resulting dynamic development in the population level is an S-shaped growth governed by reinforcing feedback in the first half of the development and balancing feedback in the latter half of the development. Note that the two loops that include stress are negative and have been added to the model, causing this shift in feedback loop dominance. Moreover, we may modify the carrying capacity to see how the growth in the population is limited by that capacity. The model is now sensitive to the carrying capacity and able to replicate the S-shaped population growth that constitutes the first phase in our problem development. It is, however, not able to replicate the last one that constitutes a sharp population decay. Once again, therefore, we continue the modeling process. Finally, we may introduce a gradual decline in the carrying capacity resulting from an environmental degradation, say from pollution or climate change. To do so, we use the switch at the top of the screen to activate a gradual decline and use the slide bar appearing to set the target carrying capacity towards which the carrying capacity will be heading over time. Observe the resulting decline in the population level and compare that result with the reference mode presented initially. The model now successfully replicates the entire problem development, and the problem has been identified. We can now address the challenging question, how may we avoid the abrupt population decay? To do so, we would move on with our modeling process. Clearly, the answer lies in stabilizing the carrying capacity at a desirable level. We consequently would consider the carrying capacity as a stock and would ask ourselves what constitutes the carrying capacity and what flows would contribute to its development over time. If water availability is considered an element of the carrying capacity, then the provision of rain as well as drought would play significant roles. If temperature stability is considered an element of the carrying capacity, then the temperature rise and fall would play important roles. This indicates how additional modeling may lead us to the roots of the problem and to potential solutions. This concludes our brief presentation of the system dynamics approach. If the system dynamics approach based on modeling, simulation, and analysis is of interest to you, please consider taking this course at Riga Technical University.